Hi, welcome to another lecture on deep learning. We have come to the almost to the end of that chapter, the subject, and we are in the last unit, the fifth unit, which is practical methodology. It is in the chapter 11 of the textbook, deep learning textbook by Ian Goodfellow. So far, we have seen that in the first unit, we talked about the introduction to deep learning, what is the necessity of deep learning. In the second unit, we talked about the regularization and the regularization strategies like L1 regularization, L2 regularization, then dropout, then data augmentation, then gradient, then unsupervised learning. With after that, in the third unit, we talked about convolutional neural networks, which are very important for image data. And uh, in a convolution neural network, we have seen what is pooling, what is uh, padding, and what is a stride, and how we can use that for image classification and other important aspects. And in the previous fourth unit, we talked about RNN, where the deep learning is used for NLP related tasks. And we have seen what is RNN, what is back propagation in RNN, what is forward propagation, and how the memory is continued in RNN from one unit to the other. And then we have also talked about the disadvantages of RNN, which is with two limitations that we have seen. That one is vanishing gradient problem, another is exploding gradient problem, and what are the strategies to mitigate those two problems also we have seen. Then we have seen the structure of LSTM, long short-term memory, and how the three gates, forget gate, input gate, and output gate are used, and what are the equations related to them we have discussed. Then finally, we have seen the gated recurrent unit, and we have seen the two uh, gates. One is reset gate, another is update gate, and how those two are used, and the particular equations also we have seen. With that knowledge, let us move to the last chapter, which is known as practical methodology. So, you are also doing your final year projects, and this chapter will help you to tune your project. So, when you apply deep learning techniques to any given particular task, knowing an algorithm, knowing the principles is not sufficient because every machine learning or deep learning engineer has to take certain decisions. One of such decision is which algorithm should be chosen. There are many algorithms, right? If it is machine learning, you have SVM, you have decision trees, we have linear regression, we have polynomial regression, and in decision tree, we have bagging and boosting algorithms. Then in unsupervised learning, k-means algorithm, in supervised k nearest neighbors algorithm. If it is deep learning, you have CNN, you have RNN. Then in CNN, different architectures are there, Inception Net, Google Net. All these, in among all these available, one important decision that you have to take is how to choose an algorithm for a given particular application. So even when you're doing a project, so this is the first decision that you'll be taking. Then secondly, how we can monitor or how we can respond. Suppose we are doing certain project or certain things, and then you got some results, and how to respond to those parameters and how to improve the performance. That is what another decision. Then you have particular data. For example, you have 1,000 samples of data. The question is whether to gather more data or is it sufficient? If you gather more data, will there be any guarantee that your model performance will be increased? Then model capacity. Model capacity means the extent to which it will cover the features. It should be increased or decreased, or which regularization uh, features we should take, whether we apply dropout or whether we apply L1 or L2 or data augmentation, whether we should apply or we should abstain from applying those things. Then shall we improve the optimization of the model for choosing different parameters? So these are the different decisions. So the practical methodology chapter, which is written by Anne Goodfellow and his both of his friends or colleagues, they gave recommended four step practical design process. So the first step is determine your goals very clearly. So there should not be any ambiguity of determining our goals. What we mean our goal, what is our problem, and what is the error metric we will be using. What are the error metrics? You know, accuracy, precision, recall, mean square error, mean absolute error, or loss function, hinge loss, Huber loss, KL loss, de Gale divergence. Among all these, which should be taken? If you remember, we have seen that if it is classification, generally accuracy will be the metric. If it is in general, not that every problem will be depending on accuracy, we'll see in the future classes that in some situations accuracy may not be the perfect metric. Then if it is a regression problem, then we'll be using mean square error. So then the second question is, once you choose the error metric, what should be the value? How much, suppose you are choosing accuracy. So what is your target value? You want to achieve 95%, 97%, or 98%, or 99%? It should be clear. So all these goals should be specific and clear. And these goals and error metrics will depend on the problem. So they should be driven by the problem data. That is the first step. What is the first step? Determine your goals clearly and specifically. Secondly, establish a working end-to-end pipeline. In the beginning itself, have a complete working structure. For example, you are doing CNN, choose your convolutional layers, choose your pooling, choose your padding, choose your stride, choose your number of fully connected layers, number of hidden layers, and see that it will work in the beginning. Then you can fine tune. If you want every parameter to work and then you want to combine, it may not happen. So build a complete, it may be very simple, it may be very primitive, but build a complete end-to-end version of your system. So from the input to the final output prediction, and then measure its performance. If it is not optimized, even if it is not optimized, then you can fine tune it. That is number two. Number three, design your system well to determine what are the bottlenecks, what are the problems. That means you have to diagnose, which which is what is the problem, which is limiting or reducing the accuracy or the why the accuracy is not achieved. You should be able to design, identify your problem. So your system should be so well that you can determine the problems, whether it is due to overfitting or whether it is underfitting, or is there any problem with software, is there any problem with number of layers. You should be able to identify. Then, fourthly, repeatedly make incremental changes. Just like we study in software engineering, incremental model, here also you can increment, you can add more data, you can gather new data, you can fine tune the hyperparameters. What are the hyperparameters? Learning rate, number of layers, regularization, all these are hyperparameters. Then if it is not working, you can change the algorithm. So four steps per practical design process. Number one, determine your goals. Number two, establish a working end-to-end pipeline. Number three, instrument the system well to determine bottlenecks in the performance. Number four, repeatedly make incremental changes. So with this four, we'll go further. So firstly, we'll see what performance metrics we can use in our system. So we want to have a metric for efficiency or how effectively our system is working. You may have very sophisticated, very accurate system, but certainly there will be a minimum error. There is no system without error. That is the rule of thumb. So we define an error, which is even if you have infinite training data and perfect learning algorithm, there will be a minimum error rate which will be there. That error, minimum error that will occur in spite of availability of huge training data and an excellent learning algorithm, that error is known as called as base error. So base error, it is a positive one because why that error occurred? We are saying we have infinite data. We are saying we have perfect learning algorithm, but even in spite of that, why error occurs? Because error occurs because your features may not contain all the information related to the output. And secondly, the data which you have, though you have infinite data, data generation is maybe random. Generally, it is you cannot consider, you cannot take all the data in the world. You can take only part of the data. You know, when we studied, we can take only sample data, not the whole population data. You can take only sample data. That's what we are saying. So, base error is the minimum error that will occur even in case of very perfect system. So we'll see whether we want to collect more data or not based on our error metric, and we can say whether data is required or not. So one type of metric that we'll be using is accuracy. What is the formula for accuracy? If you remember, the number of correct predictions by total predictions, right? TP plus TN by TP plus FP plus FP plus TN. TP plus FP, TP plus TN by TP plus FP plus TN plus FP. So that is the accuracy. In most of the classification problems, accuracy will give you the effectiveness of your algorithm. But it is not the case for all the situations. We cannot depend on accuracy because, for example, accuracy tells you about correct classifications, fraction of correct class, correct positive, correct negative out of the total. But in some situations, there will be some cost. For example, if you take male classification. So male classification, what is false positive? Important male will be labeled as spam. And what is false negative? A spam mail may be labeled as general mail. So if you take these two, false negative is not much dangerous. Even if our system labels a spam mail as not spam, nothing much occur. We may read it for once. But if your system sends an important mail, something like job offer or something like your report card or interview call letter, if it labels as spam, then there is a real problem. That means here it is more costly than this one. So accuracy considers both things equally. But here, in such cases, the cost of false positive is more, cost of false negative is different. So that is one case where accuracy may not be perfect metric. And then in another case, we can see that suppose we have very, very rare disease, which it occurs only in 10 lakhs. If you have only one person is affected in 10 lakhs, and when you collect your data, you may collect 1 lakh samples. And in 1 lakh samples, there is no one having that disease. So obviously what you will get? You will get 100% accuracy. So there, though you were saying 100% accuracy, that is a poor way of characterizing. So alternative to accuracy, there we have precision, recall, F score, and precision recall curves. So let us revisit what is accuracy? TP plus TN by total TP plus FP plus FN plus TN. Now this is called as confusion matrix, you know, right? We are considering a binary classification problem, and this is confusion matrix. So what is precision? Precision is correctness of the positive predictions. So it has predicted some as true positive, which is correct, and some as false positive, which is not correct. Now, what is the ratio of true positive to both of these, true positive plus false positive? This is known as precision. So it will predict the fraction of the positively predicted, that is precision. Then what is recall? The fraction of actual positives, predicted positives by actual positive. These are the actual positives, and this is the predicted positive. This is known as recall, TP by TP plus Fn. This is TP by TP plus Fp, and this is TP by F. Here, what is the ratio? Ratio of positive correctness of the positive predictions. Total positive predictions are these, and this is the correct. And what is recall? Recall or is also called sensitivity. How many true positives are detected out of the total? So combining these two, we have F score. F score is 2 into precision is a harmonic mean. 2 into precision into recall by precision plus recall. So with this, this is more a balanced version of metric than the simple accuracy. That means your system, if it performs well both on precision and recall, then only your F score will be high F score. And then you can estimate the performance of the system. And another way is doing precision recall curve, drawing a curve, and if the curve is closer to the upper right corner, this is a better model. If area under the curve can be used as summary metric. So this is about the metrics that we use. And then we have also, you have another thing, coverage. Say, sorry, you have 5 units, but in the final examination, if you study only 1 unit and if all the questions come from 1 unit, you may get 100 marks. But the thing is, you didn't cover all the 5 units. So even our system, if it covers only few samples, then automatically you will get 100% accuracy. But the coverage is poor. So we want high coverage. And apart from this, we have other metrics also, click-through rates, satisfaction surveys, domain-specific criteria. So without a clear metric or target, it is very hard to evaluate whether our system is performing better or not.